Welcome to The Explainer. Today we're cracking open the ancient science that turns ordinary rock into the extraordinary metals that build our entire modern world. It all really boils down to one simple but kind of mind-blowing question. How do we get from a plain old chunk of Earth to something as complex and powerful as a rocket engine part? The answer? It's a field called metallurgy. And you can think of it as this amazing mix of art and science, the craft of unlocking metals from the ground and getting them ready for, well, everything we build. It's part chemistry, part engineering, and honestly, it's pretty cool.
So let's actually follow that journey. How does a seemingly worthless piece of rock transform into a pure, valuable material that's ready for action? All right, first things first, concentration. See, the metal we're after is always mixed in with a ton of just worthless rock. So the very first step is a massive cleanup job to get rid of all the junk.
We have to separate the good stuff, the ore, from all the worthless rock it's mixed with, which has a great name, the gangue. It's kind of like trying to find a needle in a haystack, except, the haystack is the size of a mountain.
So how do you do it? Well, one way, especially for heavy ores like gold or hematite, is gravity separation. And it is literally panning for gold just on an insane industrial scale. A powerful current of water washes away the lighter gangue, leaving the heavier, valuable ore right there for the taking.
But what if the ore is actually lighter than the waste? Well, for things like lead or zinc sulfide, the process gets really clever. You basically give the rocks a bubble bath. No, really, the valuable metal bits are made to hate water, so they cling to these oily bubbles and just float to the surface in a froth, where you can literally just skim them right off. And then, if you're lucky enough that your ore happens to be magnetic, like chromite, the solution is beautifully simple. The crushed ore just gets passed over a giant electromagnetic roller, which snatches the magnetic ore right out, letting all the non-magnetic junk just fall away. Easy. Okay, so we've concentrated the ore. We've got the good stuff. But the next challenge is to break the super strong chemical bonds that are still locking our metal inside the mineral. And yeah, this is where we turn up the heat. A lot. The whole goal here is to use some seriously intense heat to convert the ore into a metal oxide. Why? Because it's a much easier chemical form to work with. And depending on the ore, that means either roasting it with plenty of air or heating it up in a process called calcination, which happens without any air at all. And that brings us to the main event, the fiery heart of this whole journey, smelting. Inside a massive furnace, we use incredible heat to finally break down that metal oxide and release a crude, molten version of our metal. Now, inside that furnace, there's this little chemical drama playing out with 4 key characters. You've got the metal oxide, which holds our prize. You add a reducing agent, usually carbon, whose job is to basically steal the oxygen away from the metal. Then a flux is added to bind with any leftover impurities. And the result? You get slag. That's the molten waste that's left over. And choosing the right flux? That is absolutely critical. It's specifically designed to react with any of that leftover gangue. This chemical reaction creates that liquid slag, which conveniently floats right on top of the much heavier molten metal, making it super easy to just skim the waste right off the top. Okay, let's get to the final stage. The metal we get from smelting is still kinda crude. It still has impurities. But for today's high-tech world, from microchips to jet engines, we need mind-boggling purity. Just how pure are we talking? Well, take the Mond process for refining nickel. It can get that nickel to 99.5% purity. Think about that for a second. That's getting rid of nearly every single unwanted atom to get the perfect properties for whatever you're building. And that's exactly what refining is all about. It's using really clever chemistry to target and hunt down those last few pesky impurities that could totally compromise the metal's performance. And getting to that kind of purity, yeah, that takes some seriously specialized methods. It's not one size fits all. Each metal has its own little trick, from using chemical vapors for nickel to the Van Arkel method for titanium, or even just pure electricity to refine copper. Every process is tailored to get to that ultimate level of purity. So, after all that work, all the concentrating, smelting, and refining, why does it all matter? Well, let's take a look at how these metals literally build a world you're living in right now. Just think about aluminum. It's lightweight, it's strong, and it doesn't rust. And because of the metallurgical processes that create it, it's become absolutely essential for everything from the planes we fly in to the pots we cook with, and even the simple foil that keeps our food fresh. But here's the thing. This level of mastery, it isn't new. Not at all. In Delhi, India, there's an iron pillar that's been standing for over 1,600 years, and it hasn't rusted. For centuries, nobody had any idea how that was even possible. This pillar is just an incredible testament to the advanced knowledge of ancient Indian metallurgists. They created something that, by all the rules we know, simply shouldn't exist.
It actually took modern science to finally figure out their secret. Turns out, the ancient metallurgists had unintentionally created this unique, ultra-thin protective film on the surface, a compound called mesawite. And that tiny layer stopped rust dead in its tracks. You could almost call it a 1,600-year-old piece of nanotechnology.
So, from ancient pillars that defy time to the advanced alloys that are going to take us to the stars, metallurgy has always been the engine of human progress. The journey from rock to rocket is still going on, and that leaves us with one really exciting question. What new materials and what new possibilities are still just waiting to be unlocked from the Earth?